Today we're taking a look at simple harmonic motion, more specifically at pendulums and springs. So first let's take a look at what simple harmonic motion is. Simple harmonic motion can be defined as any motion in a system or object that repeats itself at equal intervals of time. This system or object is known as an oscillator. This time interval of time is known as the period. The period can also be defined as the time taken for one cycle. A cycle is the complete motion that is being repeated in a simple harmonic motion. A simple harmonic motion can be defined as, you guys get the point, period and frequency. Whereas period is taken usually in seconds for one cycle, the frequency is defined as the number of cycles that occur in 1 second. For this reason, they are inverses of one another. Even from the definitions, you can tell they're inverses because frequency is number of cycles per second and period is numbers of seconds per cycle. So frequency, F is frequency and is measured in hertz. Capital letter T is period and is measured in seconds. If a given number of cycles and the time it takes to complete those cycles, you can calculate period and frequency. Therefore, F is number of cycles over time, and T is total time over number of cycles, where F is frequency, measured in hertz, and T is period, measured in seconds. Also keep in mind that if you find frequency, you can just do 1 over F to get period, and if you find period, you can just do 1 over period to get frequency. Here's an example. Steph Curry is doing a dribble drill where he bounces a basketball 15 times in 3 seconds. What is the ball's frequency? Well, frequency is number of cycles over time. So that would be 15 divided by 3, which would be 5 hertz. What is the ball period of motion? Well, period would be time over number of cycles. So that would be 3 divided by 15, which works out to 1/5, which if you got a decimal answer, that would be 0.2 seconds. So let's take a closer look at pendulums specifically. Now, pendulums and springs are not the only things that go through simple harmonic motion, but for today's class, those are the 2 things that we are going to look at. So a pendulum is a weight attached to a free pivoting rod or spring. The angle of release, in order for it to be simple harmonic motion, must be less than or equal to 10 degrees from the vertical. So the equation for period is T equals 2 pi times the square root of length over gravity. So make sure you guys are pausing, rewinding, rewatching, whatever you need to do to get these equations. These are the equations that you're going to use on your quizzes and tests. So T is period, usually in seconds. L is the length of the pendulum, usually in meters. And G is the acceleration due to gravity, which is 9.8 meters per second squared. Now you'll notice that I do not make the 9.8 negative. You don't want to try to take the square root of a negative number, so just leave it as a positive 9.8. 2 pi is not really a variable. It's 2 times 3.14, which is approximately 6.28. And so the only variables that you have are period and length. All right, those are the only 2 things. So the only thing that affects the period of a pendulum is the length of the pendulum. The mass doesn't affect it. The angle that you release it from doesn't affect it unless it's more than 10 degrees. Because if it's more than 10 degrees, you can't use this. Springs and simple harmonic motion. If a mass is attached to a spring and is pulled and released, it will undergo simple harmonic motion. This is, of course, assuming you're not overstretching the spring to where it's deformed or anything like that. The equation for the period is very similar to the equation for period of a pendulum. It is t equals 2 pi times the square root of m over k. In this case, t is the period, usually in seconds, m is the mass of the object, usually in kilograms, and k is the spring constant, which is usually newtons per meter. 2 pi, again, is not a variable. It's just approximately 6.28. Now, with this, there's two things that affect the period: the mass of the object and the spring constant. Now, you're going to have to stretch your algebra muscles to be able to solve for mass and solve for the spring constant, but we can do it. You just need to ask questions in class, and I'll be more than willing to help. Lastly, we're going to look at springs and force. Now, this doesn't really have to do with simple harmonic motion. It more just has to do with the force. But at the same time, since we're covering springs, figure we'd add this in there. So when you pull on a spring, you can feel a force pulling back. There are two things that determine how strong this force is: the length of the pull, which is x, and the stiffness of the spring constant k. The equation that explains this occurrence is F equals kx. When hanging a weight on a spring, remember that the force the object is applying to the spring is going to be equal to F equals mg, right? So if you're doing a problem where they're asking you to find spring constant, for example, and they don't give you F, you would probably use the weight of the object as being F. So you'd end up with mg equals kx. The same is true if they gave you the spring constant and asked you to find the length that the spring is stretched or compressed.